All right. So welcome everybody to our final lesson of Hoon Academy, lesson 8. So in this lesson, we will be going over how to build production quality code and look towards what's in store for the future. So for this lesson, we are going to start with this following block of code. Let me put it in the chat for you guys, and let me know if you can see that. So we're going to start by taking this code, saving it as a generator. We're going to go to our FakeZod, base desk, and the gen folder, and we're going to save it as primes. Yeah, I typed there. One more time. Zod, base, gen, primes.who. And what this piece of code does is, well, we'll see in a second, run commit base. And if you give it an input like less primes 10, going to return all the prime numbers up to that number 10. So you could do 100. And those are all the prime numbers between 0 and 100. All right. So if we're looking at this piece of code for the first time, how do we interpret what's going on? We can read this Hoon and try to understand, but maybe there's something that the author could have done to make this process easier for us. When building production quality code, including comments helps both yourself and others understand your code better. To write comments, simply use this col. This makes everything that you type after it on the line turn into a comment. That's not parse this code. Note that this doesn't multi-line, so you have to make a new col for each new line that you want to type. You can actually also put a col after a line of code like this, but that's discouraged style these days, but it is possible. All right, so let's look at our fully commented version of this primes.hoon. Here we are. Now we have a lot of comments explaining exactly how this code works. So what is going on? Primes.whom outputs a list of prime numbers between 2 and the input number. Here we have a gate, takes an input number, and here we're doing tisfaz output. We're creating the output list. We start by using gulf 2 to the input. So this output list starts as a list of all the numbers between 2 and your input number. Then we pin this n, which is a counter, to filter out all the non-primes from this list. We have this bar hep, which is a trap for recursion, right? What is the recursion doing? Well, we're saying if n becomes the input number, then return the output list. If n has not reached the input number, then we're going to recurse with output list filtered out by every number that's divisible by n, except the number that equals n, and then also recurse with n incremented by 1. So say we're getting the number 10 as an input. We're going to create a list of all the numbers from 2 to 10. We're going to say, okay, first let's filter out everything divisible by 2. Increment 2 to 3, then filter out everything divisible by 3, then increment 3 to 4, filter out again, and so on and so forth until n reaches the input number 10. So that's basically how this piece of code works. So any questions on making comments or this primes code? All right. So when we're building complex code, there's a variety of tools that we can use to make sure that things are working. So for example, in our primes code, it wouldn't make sense if the input was 1 or 0, even though that's allowed under PAT-UD, because the smallest prime number is 2. So let's say we want to cache that case and we want the code to actually crash on that input. We can use this rune called whatgar. What does this do? Well, whatgar takes 2 children. If the first child evaluates to true, just gonna compute this like nothing happened. And if this evaluates to false, then it'll crash. So basically this is saying, I assert this is true. If it's true, I can do the rest of this. If this condition is false, then I have to crash and not evaluate the rest of the code. All right. So here's another version of our primes. This time we have no comments just for brevity, but it's the same code as before. So let's look at this line 3. We are saying what gar, and the condition is GTH input 1. So we're asserting that the input is greater than 1. And if so, we're just going to do the rest of our code as before. All right, so let's save this, run bar commit base again, and let's test primes 10. Does the same thing as before. Primes 1. We're going to get a failure. So next run, what gal does pretty much a similar thing to what gar, except it asserts that this condition is false. If this is false, then you can keep going. And if it's true, then you're going to crash the code. So how we might write this with this what gal, sorry, would be we assert it's false that want to assert it's false that the th we would like to assert that it's false that the input is less than 2, right? So same thing, run commit base, primes 10 works, prime 100 works, prime 1 gives us a failure. That's just pretty much the equivalent thing as before. We can use this rune called zap zap to just directly crash the code. So if I just go to my dojo and type zap zap, that just says Hoon expression failed. And actually, these two pieces of code are exactly equivalent. This says assert that A is false, then compute B. This says if A is false, then crash, otherwise compute B. So this is just a different way of writing this assertion. We can get some more information when a piece of code crashes by doing a zap call at the top of our code. What does zap call do? So this rune takes one child, which is just a Hoon expression. If this Hoon crashes, we're going to display a stack trace, which will help us pinpoint the source of the crash. So we add the zap call to the top of our code, run commit base, and what happens now? So, well, we were getting this stack trace before for whatever reason, but basically, let's go on. So I think my version of this ship is on an older version of the runtime, and there's has not been some updates to the stack trace. So unfortunately, this demo is not going to work at the moment, but what should happen if you try this on your Urbit ship is you put the zap call at the top, and it's going to trace, it's going to say 5 or 4, 1 to 418 is the source of your crash. So it's going to have this narrow down all the way to 4, 1. Um, all right. So basically, these numbers right here are telling you where the source of your error occurred. All right. So there's a few ways that we can make this code print messages to the terminal. So let's try this. What if we want to make it print a message when it crashes? So here's our code as before. Here we say what call if the input is less than 2, then we're going to use this sigbar rune. And this takes 2 children. It's going to print this first child to the terminal if the second child crashes. And since the second child is a zap zap, that's just going to crash. So basically, if we're in this branch, we're going to put this to the terminal and crash. So let's save this, run bar commit base, primes 1, and boom, we get crash because input was less than 2. And here we see the stack trace. So this last line of the stack trace says your crash occurred on line 5 between column 48 and column 50. So that's going to be this right here, the source of our crash. We can also always print something to the terminal. So suppose that we're debugging this code and we want to see the intermediate state of this output list. So recall that we start with this output list as a list of all numbers from 2 to the input. And then at every step of the recursion, we're removing things. We're removing everything divisible by 2 or 3 or so on, right? We want to see the progress of that. So let's do that. We can use this sigpam rune. It takes 2 children. So it's always going to print this first child to the terminal, and then it's just going to calculate the second child. So how you'd use this is like just do sigpam output inside this code. This is the first child, and the rest of this code is the second child. So this is just going to print that output to the terminal while it's going through this recursion, while it's doing everything else that it did before. All right. So let's save this and commit base. Now what happens when we run primes 10? Cool. So we got some informative output here. Here we're seeing the state of our output list at every step. So first it starts as 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes to 2, 3, 5, 7, 9. That's because you filtered out all the multiples of 2. Then we're going to filter out all the multiples of 3, besides 3, which is only 9. And then we'll filter out multiples of 4, 5, 6, 7. There's no more non-primes to filter out at this point, so that list is just staying all the way till the end until we get 2, 3, 5, 7. There's a few more neat things we can do with this logging. So we can change the color of this output. We put a single gar before it, single right arrow, then what happens? Oops, need a double space here. Now it's green, and we do 2 arrows, then it's yellow. And we can even do 3 of these to get red. So Those are the three colors that are available. Yep, pretty much. That's like the occasions that you'd use these three colors: success, warning, and failure. Yep. All right. Any questions on logging? This is the relevant line right here. All right. So if there's no questions, we shall move on. Um, in Hoon, you can save a core containing pieces of code in its arms and then import it as a library file. You may be familiar with this from other languages. Importing libraries is very common and very useful. So let's do that with our primes code. So let's make a library for it and import it and use it. A new file here. And this is going to be our piece of library code. So this is just the core with a single arm called filter. All right. So we're going to save this in base lib. This is where all your library files live. And let's call this primes-lib.hoon. All right. So let's change our primes.hoon generator. So we're going to add at the top fazlus. This is the rune to import a library file. This has to go at the top, and it's going to look for a file in the lib folder. So what we're going to do, we're going to say import primeslib. All right. And what this filter logic does is it takes a list of numbers and a number, and it filters out all the multiples of that number besides the number itself. So this is helping us do some of this logic right here, right? Filtering out this output list. So what we're going to do, we're going to replace this with filter from the primes library. This col right here is remember that's sugar syntax for tis-gal. But here we're gonna say call filter from the primes library on the output list and the value n. So there's a syntax for calling gate. This is how we're pulling this gate out of this core, this library core. All right. So let's save this. Get rid of the logging and check that it still works. Commit base primes 10. You got 2357. Nice. So we are successfully importing this primes lib and using filter from it right here. If we import the library file with this tar in front, then we can access its namespace directly. So that means we don't have to do this filter col primes lib. We can just call filter, and it's going to be able to find that in the arms here. So we change this to tar primes lib, and we change this to just filter. We're calling it directly. Let's run commit base, check that it still works, and it does still work. All right. Any questions on that? Okay. Can you paste primes? Yes, like the new version. Indeed, I can paste that for you. Here we go. And the old version was like this and like this. That's the other version. Oh, that's because you don't have the library file, which should be saved in primeslib.hoon in the lib folder. So here's the code for the library file. Drop that for you again. Yeah. That can happen. Yeah. Should be in the lib folder. Can generators import other generators? Yes, they can. You can actually import arbitrary files. We will cover that in a little bit. Okay, so you can actually import library files to the dojo as well. Unlike generators, they aren't automatically imported when you run commit base. They aren't automatically accessible, but you can import them so that you can just run code from libraries in your dojo. So here's the syntax for that. We have tis primes lib pep build file, and here's the address of the file. Okay, so I'll drop this command in the chat for you. And let's break down what's going on here. So here we're saying, let's run this build file thread. Threads are things that live in the TED folder. They're like transient utilities. Basically, this is just like a useful utility that exists. So we're running this thread. That thread takes a Hoon file and builds it and makes it available in the Dojo subject. This is the address of the file to build. This whole thing is address. This sen at the beginning is actually a shorthand. So this full expanded version is supposed to be a triple of ship, what ship you're referring to, what desk you're referring to, and what case you're referring to. And the case is a version. Usually use the most current time, like now is the most current time, right? If you want to get the most current version of the file. So this sen would actually expand to something like sample palnet base and this time. But if you want to refer the default values, you can just use this. This is saying it's in the lib folder, and this is saying the file in the lib folder is called primes-lib.hoon. The file ending on clay, it's actually a mark, so it's notated with this slash, this faz, rather than the dot. And this is just saying, let's pin the result of calling this build file and make it available under this face called primes-lib. Okay. So now we can call this library file from the dojo. So now we can just do filter call primes-lib and pass it this list of numbers, and we want to filter out all the multiples of 2 besides 2. And we're going to get our list numbers here. That formatting is because this doesn't have a typecast inside of it, but if we add this cat hat ud to make this typecast, run commit base again, run the command again to build the library again. Oh, sorry. List pat ud. So we want this to return a list of numbers, right? Save it, commit, build the file again, run this command again, filter, and now we get a nicely formatted output. All right, any questions on that? Okay, so for the next section, let's quickly cover a concept that's going to be useful. So a vase is a pair of a type and a noun, where the type describes the noun. So vases are used all over Urbit to send and receive data while clearly communicating what type the data is. This often comes up when you're being asked to compile and run other pieces of Hoon code. To make a vase, you can use this Zapgar rune that we did learn briefly before. takes one argument and approves the vase, type of Hoon, Hoon. So simple example, you zap gar zod, then you get the cell. This says type of the data is a PAP-P, and the value is 0. That's because zod is actually the value 0 underneath, right? So this is kind of breaking out this data into two parts that clearly describe what it is. If you have data in a vase and you want to extract it, you can use zap gal. It's going to take 2 children. So suppose we made this vase. We made this vase with zod in it, and we want to extract this vase back out to PAP-P. This is going to give us the zod back. You also do it like this. This makes it a little more clear. Oh, that doesn't work. This is an artifact of the pretty printer. But yeah, this is, here we have zod in the vase, and then we extract it out of the vase, we get zod back. And if we try to extract this to a different type that doesn't fit, like a PAT-UD, we're going to get a failure. All right, so pretty straightforward stuff. I'm covering this because we need it for the next section. All right, so our next section is about unit tests. So testing code is a very important part of shipping clean, high-quality software. So let's write some tests and run them for our primes generator. What are we going to do? Let's open up the File Explorer and let's make a folder in our base desk called tests. This wasn't here before, but I made this and added it. And we're going to put a file in there called primes.hoon, which contains our tests for the primes generator. Right, so I think I had this from last time, but let's go over making it again. So delete this. Oops. New file. And let's put this big piece of code in there, which represents the tests for our primes generator. Save it in the test folder as primes.hoon. And I'll put this big piece of code in the chat for you guys as well. All right, so what is going on? Let's break down this code bit by bit. Oops. So up at the top, we have this fazlus tar test. That's going to say, let's import the library file test.hoon. You're going to need this for every test that you run. So this is a standard piece of boilerplate. Using this tar test instead of just test means you can access its namespace directly. Faztiz can import any Urbit file. So here we're going to import the primes file in the generator folder, which is our primes generator, under the name primes. So import this generator under the name primes. This core has 4 arms. Each arm of this core needs to have the word test in it to make it be a test. The test thread is going to look for arms with the word test in them and run them. There's 4 arms, so we have 4 tests here. Here's our first test, test 01. All right, so what's going on in here? We're calling this gate expect eq. This is an arm from the test library that we imported here. It takes 2 vases Remember, these vases are cells of type and noun, and it checks that they're equal. It expects that they're equal to each other. So what are we expecting that's equal to each other? We expect that a vase containing a list of PAUDs of 2, 3, 5, 7 is the same as a vase containing the result of running our primes generator on input 10. So here we have a value. We put it in a vase that becomes the first argument to expect eq. And here we have the results of running our test subject, our test generator. We put it in a vase, and we expect that these two things are going to be equal. All right. So these other two tests here are pretty much the same thing. We're just testing different values for different behavior of the generator. Here we're testing that primes on 2 just returns 2, primes 50 returns this big list. We also have one test to test for code failure. So this is calling the expect fail gate from the test library. And it takes one argument, which is the code that should be producing a failure, should be crashing. We do have this bar dot right here. Recall, what is bar dot? That produces a core with a single arm. What does this do? This says, let's take our code that's going to crash. Remember that calling primes with the input 1 should crash since we added our condition earlier. We don't want that just to be like running immediately and crashing our test thread, right? We want to like store it in a way that we can pull it and run it in a controlled environment. So by putting this crashing code in the arm of a core, this delays evaluation so that the test thread can then pull it and run it in the controlled environment where it's like, okay, this can crash in this like subzone of the code. All right, any questions on that? Cool, so we can run these tests now. Save this to bar commit send base. And we added this primes.hoon in the test folder. All right. Here's a syntax to run tests. This pep test is saying run the test thread. This is a thread that lives in the TED folder. And we're going to pass it an argument, which is this file primes in our tests folder. So we're going to run this thread with the argument, which is the file we just made. All right. And what happens when we press enter? We get 1, 2, 3, 4 passes. And they also tell us how long the test took. This sen at the front is, we just saw something like this. This again stands for the location that you're at. So the ship, in this case Zod, the desk, in this case base, and the case, which is now. You can also write it out like this. In this case, this tis also is saying use my current ship, my current desk, and the current time for these values. And why did that not work? Oh, sorry, primes. So yeah, this is the same thing as having this sen in front. All right, so any questions on testing? Otherwise, we shall be moving on today. Why no /Hoon at the end of test? That's a good question. Basically, in certain situations, it like knows that it's going to be a Hoon file and it doesn't ask for the line ending. Like the test thread needs to take a Hoon file, right? But this can be a little confusing because it's just like inconsistent. Sometimes you need to include the mark, the type of the file, and sometimes you don't. But in this case, the test thread, like it always is going to take a Hoon file. So I think that's why there's no need to do this. Let's see if it still works. So yeah, so you can include that, but it also works if you don't include that. Good question. All right, any other questions? Okay, so moving on to the next section. So far, we've learned how to work with regular generators. We've wrote them, saved them, and run them, right? It turns out that what we've worked with so far are called naked generators, and most generators in the system are slightly more sophisticated versions of the generators called sensei generators. Okay, so to understand, let's look at a really simple naked generator. So what does this code do? Okay. It's a gate, accepts any noun as input, and just returns the number 42, right? So let's save this code. Um, Save this as in the gen folder as a generator and save it as test. Well, it's a little confusing. Let's save it as example. Okay. All right. So this is example.hoon. Run bar commit base. And how do we run this thing? We do less example. And this thing wants an argument, right? It has to take something. So let's just give it like anything as a input. And it'll return 42, right? Just throws that away and returns 42. If it's giving us such basic behavior, you think you might want to like not require an argument at all, but you actually cannot call this naked generator without any argument, because it needs an argument. So this is going to fail. All right, so let's write this very simple piece of code as a sensei generator. Boom. Okay, this code in the chat for you guys. So we save this version of the code, run bar commit base, and run it. This time, we can actually run it with no arguments. So let's look at this code and understand what's going on. We have this col hep up top, which means we're making a cell. The head of the cell is the tag sensei. Just remember, this is a term. And the tail of the cell is a generator. It is the gate, sorry. Inside the gate, we're not just directly returning the result, but we're returning the result inside of a cell head tagged with this send noun. And what is this send noun? This is actually a mark. This is a little tag communicating to the system that what's inside here is of type send noun. Both of these tags are metadata information that's communicated to the system. Sensei says this is a special type of generator. Send noun says this generator has a particular kind of information in it. When you run this generator, the dojo is going to read these informations and filter them out so that you just get the number 42 out in the end and not any of these extra tags. So in this generator here, the sample of the gate is just tar. That's the most general argument possible because this can be any noun, right? Any piece of data in orbit. However, sensei generators have a special structure to their sample, which gives them access to much more information than regular generators do. So here's the structure of a say generator. It's a triple of three things, right? In those three things, the first thing is itself a triple of now equals pat dA, any is this, and beak is this. So what are these three things in here? The first thing, this now, is a current time, which the system is going to pass in. And then this generator can actually access this current time of the system. You don't pass this argument in when you're calling from the dojo, but it's just there available for the generator. This any is actually environmental entropy, and this is used for randomness. Again, you don't pass it in, this is automatically passed in by the system. And finally, this spec is a beak. That's the current path, and it's also this triple we've seen before of Zod, base, and the current time. So this is just telling you where you are. This is giving you some entropy if you, in case you want to do something random. And this is telling you the current time. Here, we make a list and we specify what are the required arguments to the generator. Is a system the rest of Urbit? Yes, that is correct. So here, the second part of this triple is a list of unnamed arguments, which are required arguments. So if you put anything in here, it has to be passed in when you're calling the generator, otherwise it will fail. And here you can even specify optional arguments, or as they're called, named arguments. So if you have an optional argument, you can call it with, hey, I want to turn this option on with input A, B, C. I want to turn this option on with input 1, 2, 3. Or you can call them without. So optional arguments. When you're specifying a sensei generator, you can customize your sample to use any part of this, none of it, all of it. So how you do that is you just put a tar on something that you don't need to reference, right? So these are all like different types of samples that can fit this triple structure. So if I just put a tar for the whole thing, that can be a valid triple. So that's just saying I don't care what's in there. You can say I just care about the current time in my generator. I don't care about the any or the beak or these arguments. You can say I don't care about these three things, but I do care about two mandatory arguments, which are text and planet, and no optional arguments. You can say I don't care about these two, I just want one optional argument. Or you can have all this stuff, right? So as long as the structure here can validly contain this structure, it's fine. So basically, say generators are going to augment the power of our regular generators by letting us access useful system information, allowing us to use randomness, and letting us use optional arguments. All right, so let's see an example of this. Let's see an example of using a say generator to write something that's random. Okay. This any is a random seed, which is just a very large number, which is passed to Urbit from Unix's random number generation. All right. So let's take a look at this piece of code right here. What's going on here? Well, let's first try it out. Let's save this as dice.hoon in our gen folder. Say generators go in the gen folder. Then can run var commit send base. And what's going on? So it has one required argument, n, and one optional argument, bet. What it's going to do is it's going to generate a random number between 0 and that n input number. So it's like rolling an n-sided dice, right? So now we committed, we can do less dice 6, and you get 2. And also prints out this text saying you won $0. Okay, but maybe we want to bet some money. Oops. Oh, there. Ah. So we need this comma right here. Boom. I rolled a 9, multiplied my $100 bet by 9. You won $900. This is a very nice bet because you win money every time. All right, so what's going on in this code? Let's break it down. Here we have a head tag. We're saying this is a say gen, right? We're making this a cell of the tag sensei and the gate. Here inside, we also have this head tag, which says the output of the generator should be tagged with the mark send noun. Here we have our sample to the say generator. Remember, this has a triple structure, right? First part of the triple is current time, the entropy, and the peak. We have one required argument, which is n, and one optional argument, which is bet. Here, we are generating a random number between 0 and n, and we're pinning it to the face of roll. Here, we're printing a message to the terminal saying you won roll times bet dollars. And finally, we're outputting the random number. So that's how this code works. Yes. Yep, if you don't use these, we're not using these in this code. So let's just try these out. Since we only use the any, right? So let's do that. Run commit base to save our code. And make sure it still works. When we don't pass in the optional argument, it still has a value for it. So bet still has a value, it's just bet has become 0. That's because it uses a bunt of this when you don't pass anything in. So yeah, now we're generating random numbers. All right, any questions on that? Cool. So does that make it more efficient? It doesn't make it more efficient, but it maybe is a bit nicer to read. Because it's just for reading the code, basically. Like now I can look at this sample of this say generator and be like, okay, here are the things I care about. And if I had left these in, if you leave these in, it doesn't affect the logic of the code at all, but it just is data that you don't use later. So yeah, but it doesn't affect the logic or the speed in any way. Okay. Any other questions on this? Can we make it recursive? What do you, yes, you can definitely put recursive logic in a say generator. Um, would you want to do something like making a lot of random numbers? Is that what you're thinking of?
How let's say we have a certain a certain amount money, and we want to the bet to take into account uh the amount of money that we already have, so that we don't lose it all. So we
Mm-hmm.
reduce it if we
Mm-hmm.
lose too much.
Mm-hmm. So to do that, you would want to have like a stored state of like, here's how much money I have, right? You want to be able to reference that somewhere, right? And that actually ties into the next section, which is like, how does Urbit actually store data? Like how is data, how is the state of your Urbit computer stored and modified? So in a generator, it's just a transient computation. So there's not really a way in here to be like, hey, I want to store that I have $100 in this generator somewhere because I mean you could like pin it, but it's like every time this runs, it runs and then it's done. It doesn't have any history, doesn't have any memory. So for the application you're thinking of, I think that might be that's not exactly the use case for a generator. Generator is just like a script that runs, you know. Does that make sense?
Yeah.
Yeah, you can definitely do much more sophisticated stuff with this. You can have recursive logic, but if you want to reference a number that's like static, stored somewhere, you'd have to use other parts of Urbit for that. All right, so there's no more questions. Let's take a moment to look ahead to what comes next in App Academy, which is our course for building user space apps in Urbit, and Core Academy, which is our course that teaches you comprehensively about the whole system. All right, so, oh, oh, I'm sorry. I should quickly go over how this random number was generated. All right. So what's going on in here? Um, this is similar syntax to what we saw in last lesson. We're calling the rad arm of the OG door with sample any. This any is the environmental entropy. It's basically a big number. This creates a gate. That gate takes a number and returns a number between 0 and that number. So you could even, since this any is just a large number, you can even put anything in there. So you can even, like, if you just do, you can just cast any to a pat, you can just see, like, this is just a large number that is changing all the time. But you can use any number as a random seed. It doesn't have to be this particular one. This will not make it random, but you can do this. So let's call the rad arm of the OG door with the seed 0. This creates a gate. We're going to call that gate on the value 100. And we get the number 5. Let's use a different seed. And there's no randomness here because if you keep doing this, you just keep getting the number 5. But if you call with a different seed, like 222.222, you get a different number between 0 and 100. Does that make sense? How this randomness is working? As long as we change the seed, maybe the last digit doesn't matter. There we go. Different number. Different number. Different number. So yeah, that seed, basically it takes a seed, does a very confusing series of calculations and gives you the random number in this range. All right, so that's randomness. Let's now move on to our final section of the class. So let's look ahead to what's going to come next in App Academy and Core Academy. Urbit is a state machine. This means that its entire functioning can be understood as a system which has some state. That state receives some input, maybe produces some output, and then it transitions to a new state. Right? So you have old state, you get some input, move to a new state, maybe produce some effects. And you can do this as long as you want, right? So then you have this new state that can receive some input, and then you transition to another state. That pretty much describes the functioning of every operation that's occurring on your Urbit computer. Since every substantial piece of code in Urbit is a core, in practice, this looks like a pair of input and some core transitioning to a pair of possibly some effects and a new core. And you do this on and on for every computation that's occurring. So let's see a basic piece of code that models how an Urbit app, or even your entire Urbit system, stores and makes changes to itself. So this tiny agent code right here, I'll put in the chat for you guys. This makes a simple model of a bank account app. Right? So here's a code. Let's break down this code. What's going on? So this code is a door. It has a sample, which is balance, which is a pat UD. Door is a core with a sample, several arms. Has an arm called this. This arm is actually a convenience notation arm. So it's saying, let's refer to dot with this. This dot means a subject of the current computation. And recall that a subject of a computation involving an arm is this whole door. So this means that we can grab this entire door by referring to this this. We can use this notation in these other arms that we're writing. If we ever need to reference this entire door, we can use this. On init, this is for initializing our simple app. The on init arm takes a gate. This gate takes a number, amount, and returns this door with the balance value set to amount. And this syntax here is a sugar form of send is. So we're saying, let's make a new door with balance set to amount. This onPoke arm is for handling inputs to the system. So what does it contain? It contains a gate as well. This is saying the sample of this gate is saying the input should be a cell of send add and some amount or send sub and some amount. Right? So we're saying the input should be a cell of two things. Head is a tag of send add or send sub, and the tail is an amount. Here we have a switch statement to do different logic depending on the tag. If the tag is send add, then we create a new door with balance changed to the current balance plus the amount. If the tag is send sub, create a new door with balance changed to balance minus that amount. And that's the entire logic for the onPoke arm. So the important thing here is that all of these arms are returning a new version of the door with some changes made. And finally, we have this onPeak arm. This is for reading the state of our basic app without making any changes. And that is just going to return the value that's stored in balance. All right. Any questions on that? So how do we use this tiny agent door? We start with a door, then we call an arm to make a new door with the state changed to something else. We do this repeatedly, and then maybe we call the onPeak arm to read what the state is. So here's an example of using this basic agent model. So what's going on in this code? We're setting our door as a subject. With that as a subject, we're going to do this. What is this? We're creating a new door by calling the onInit arm with the value 100. This expression is going to create a new version of this, but with balance set to 100. Then with this new version as a subject, we're going to call the onPeak arm of this new door. And then what's that going to give us? That's going to give us the value 100 because we set the balance to 100 and looked at it. We can do a bit more complicated set of operations where we are calling the onPoke arm. So here's the same thing. We set the original door as a subject, create a new door with balance set to 100. Then we poke that door and subtract 3 from the balance, creates a new door. We poke that door with 20 added to the balance, creates a new door, and then we call the onPeak arm. And that gives us number 117. Instead of chaining all these tisgars, we've done this chaining a little bit in lessons 5 and 6. This just is repeatedly saying set something as a subject, then do something with it, right? We can actually use this rune tissig. This tissig is going to let us do all these with just one rune. It takes several arguments, an unlimited number of arguments, and you close it with this tis. Basically saying, with this as a subject, do this. Then with this as a subject, do this. Then with this as a subject, do this. So it's basically going to make this chain composition much simpler. So we can rewrite our above series of operations in this code. So we have tissig at the top. First argument is our original door. We're going to call onInit 100 on that, make a new door. With that as a subject, we're going to call onPoke. That as a subject, we're going to call onPoke, and then we're going to call onPeak. So same series of operations, just wrote it a little simpler. All right, so this door and how we're using it, the main idea is that we're calling an arm, it's making a new version of itself with some changes. And then we can call an arm again, make a new version repeatedly. And then also we can also read the state of this thing without making any changes to it. This is a simplified version of a pattern that you'll see all throughout App Academy. And this is basically how Urbit apps, the Urbit system stores data. All right. So this brings us to the conclusion of the course. As far as entire operating systems and network protocols go, Urbit is very small and simple. And as a Hoon Academy finisher, you have a good basis for starting to understand the entire system. Urbit is a growing and evolving system that's still under construction. And don't consider anything you've learned in this course to be frozen. This is early stage open source software. If there's something you don't like, if there's something you think can be better, just jump in and change it. It's important to cultivate a sense of agency because you, the Hoon Academy graduate, will be essential for the future of this project. You've hopped on the ride to making new foundations for the internet, and you can help us steer too. We have a grants and bounty system that awards stars, which are like Urbit land, to those that complete projects. This is a great way to get noticed and work your way up in the ecosystem. And that's how I personally got on the path to working for the foundation. If you ever want to discuss what to do next on the network, definitely reach out and I'm happy to help guide you through the options there. So it's been such a pleasure having you guys in the class. I really look forward to having you around the network and at our Urbit events. And I'm really excited to see what you're going to build with your new skills. So thank you, everyone.